Hello, student, and welcome for the machine design 2 lecture series. We have discussing on topic that is a flywheel. In previous lecture, we have discussed the basic theory of flywheel, how the maximum that fluctuations is occurred, how we can calculate the energy variation. Then we have also discussed the manufacturing point of view, what are the different dimensions, how we can calculate it, how different stresses, how we can going to design, then the coefficient of fluctuation in both cases with the single flywheel and with the multiple flywheels we have seen. Now in this lecture we will discuss on the numericals. Okay, so let's start. A punching press is 35 holes per minute in a plate using 10 kilonewton per newton meter of the energy per hole during each revolution. Each piercing takes 40% of the time needed to make one revolution. The punch receives the power through gear reduction unit, which is in the turn is fed by the motor driven by belt pulley is 800 mm diameter and turn at 210 revolution per meter. Find the power of electrical motor if the overall efficiency of transmission unit is 80%. Design the cast iron flywheel. Here the material is given, cast iron is to be used for punching machine of the coefficient of settleness of 5 if the space consideration limitation to the maximum diameter is 1.3 meter. Okay, so allowable stresses of the material is given, tensile stress is given, the density is given. What is given? Basically, first note it down. We have to hold how many holes we need to punch, that is 35 holes per minute. How much energy per punch is required? 10 kilonewton meter. Okay, what is the diameter of pulley belt drive which is used? That is 800 mm. What is the speed? That is 210 rpm. How much the efficiency it is? That drive, that is 80%. Now how we can find out the value of CS? 1 upon CS is equal to slenderness ratio, that is one fifth, oh sorry, 1 upon CS is equal to 5, that is slenderness ratio. So CS is equal to 1 by 5, that is 0.2. Now how much maximum diameter, that consideration, space consideration are given over here. So maximum capital D is 1.3 meter, tau is 50 megapascal, sigma T is 4 megapascal, and rho is 7200 kg per meter cube. Okay, let's start to solve. First, the power for electric motor. We are using the energy for piercing the hole per minute. Okay, the energy which is required. The number of holes are 35 multiplied by the energy used per hole. So the total energy is required for punching 35 holes is nothing but 35 350 kilonewton per minute. Okay, so the power needed for electrical motor, that is nothing but energy used per minute divided by 60 into efficiency, that is 350 into 10 raised to 3 divided by 60 into 0.8. So how much power is required? That is 7.292 kilowatt. Now you can select the motor. Okay, you can select the motor from PhD page number 8.125. Now next one, the design of cast iron flywheel. Okay, First of all, let us consider the maximum fluctuation of the energy. So as the overall efficiency of the transmission is 80%, so the total energy to be supplied during each revolution is nothing but, that is energy transmitted to each revolution, that is 10,000, that is 10 kilonewton divided by 0.8. Okay, so actual energy is required, that is 12,000, 12.5 kilonewton meter. That much torque or energy is needed. So we should calculate the velocity of that belt for calculating the tension in the pulley. So V is equal to pi dn by 60, where the diameter of pulley is 800 mm and speed is 210 rpm. So the velocity is 528 meter per minute. So net tension or pulley action on the belt is equal to P into 60 divided by V. Okay, power, that is 7.29 kilowatt is there. So it is nothing but 7,292 into 60 divided by velocity, that is 528. So the net tension is 828.6 Newton. Okay. Now, as we know that the each piercing takes 40% of time to make one revolution. Therefore, the time required for punching hole is equal to 0.4 divided by 35. So how many time is required? 0.0114 minute is required to punch one hole. The distance moved by the belt during the punching hole, that is the velocity of the belt into the time. Okay, so how much distance it can be rotated, that is 528 multiplied by 0.0114, that is 6.03 meter. So this much is the distance which is moved by the belt during the punching of each hole. Now the energy supplied by the belt during the punch hole is EB, net tension into the distance traveled by the belt, that is net tension, which we have calculated 828.6 multiplied by 6.03. The energy supplied by the belt during the punching a hole is 4,996 Newton meter. Thus, the energy to be supplied by the flywheel for punching during the each revolution, or you can say maximum fluctuation of energy, is nothing but ET minus EB, that is the energy required, actual transmitted, and the energy actually utilized. Okay, so that difference, that fluctuation is calculated by ET minus EB, that is 12,500 minus 4,996. The fluctuation of energy is we get, that is 7,504 Newton meter. Now we need to calculate the flywheel mass of the flywheel. The m, small m, is the mass of the flywheel ring. Now considering the maximum flywheel diameter is 1.3 meter, therefore from empirical relation, the capital D is equal to 1.2 times of m. Okay, so, or you can say R is equal to 0.6 times of m, that is a mass. Now we know the angular velocity omega is equal to 2 pi by 60 and is equal to 210. So the omega is equal to 22 radian per second. Maximum fluctuation of energy delta E is equal to m r square omega square into Cs. We know the value of R in terms of mass. We know the value of omega. We know the value of Cs. So putting all the values, what we get, we know value of delta E also. So putting all the values, we get mass m is equal to 215.3 kg after solving this equation. Now cross-section selection for the mass. Generally, it is considered as elliptical. So B and D major axis and minor axis values that we have considered. So B is the width of the flywheel ring, which is 2 times of the thickness of the flywheel ring. So hence cross section of the ring A is equal to B into T, that is 2 times of T into T. So 2T square is the area if we consider B is equal to 2T. Now we know the equation of the mass flywheel ring. M is equal to A into pi D into the rho. Okay, so mass is 215.3 is equal to A into pi D into rho. A is equal to 2T square. Pi D is equal to 1.2 meter, which is maximum we have considered. Density is given 7,200. So putting all the values, what we get, T is equal to 0.065 meter, that is 65 mm. And the B is equal to 65 multiplied by 2, that is 130 mm. Now next, calculating the diameter and the length of the hub. Small d is the diameter of a hub, d1 is the diameter of shaft, and L is the length. Now diameter of shaft we can calculate based on the turning moment, that is a mean torque transmitted by the shaft. So that torque we can calculate P into 60 divided by 2 pi n. That torque is equal to 331.5 Newton meter. We are assuming that the maximum torque transmitted by the shaft is twice the mean torque. Therefore, the maximum torque transmitted is twice. That is, T max is equal to 2 times of T mean. Okay. So the maximum torque which is transmitted is 663 into 10 raised to 3 Newton mm. Okay. Or you can say 663 Newton meter. Now, T max is equal to pi by 16 tau d cube. That is a formula we can use and calculating the diameter of the shaft. So putting all the values, what we get, d1 is equal to 40.7, that is a calculated value, but 40.7 is difficult. It is not possible each time to manufacture that much diameter. We can choose the standard bars available, and we have to increase some diameter so that it can withstand that much torque. So modified diameter is 45 mm. Now based on the empirical relation, we can calculate the diameter of, that is 2 times of diameter of shaft, that is 45 multiplied by 2 is 90 mm, and the length is equal to, L is equal to B, that is 130 mm. Now cross-section dimensions of that elliptical arms. Material is a cast iron, that is the elliptical cast iron arms. So A1 is the major axis, B1 is the minor axis. B1 is equal to 0.5 times of A1, that is assumptions. And we are considering the number of arms are equal to 6. So the maximum bending moment in the arm at the hub end, by considering that the arm is considered as a cantilever beam. So M is equal to T divided by R into N into capital R minus small r. That is radius of flywheel minus radius of hub. Okay, so putting all the values, what we get 663 divided by 1.2 into 6 into bracket 1.2 minus 0.09. The M maximum bending moment is equal to 102.2 Newton meter. Now the section modulus for the arm, as it is elliptical, so Z is equal to pi by 32 into B1 into A1 square. Okay, so we know that B1 is equal to 0.5 times of A1. So rearranging this equation, what we get, 0.05 into A1 cube. Now the bending stress sigma B, okay, here it is written as sigma T, but we are generally denoted by sigma B, or you can say tau, sorry, sigma B. it's a 4 times of m by z. Okay, it's a 4 times of m by z. So putting all the equations values of m and z, what we get the a1, all values we can get in the form of a1. So the major axis for this elliptical arm is equal to 80 mm, and for minor axis of this elliptical arm is, it's a half of that, so it's a 40 mm. Now calculation of the dimensions of the keys. Now we can select based on the diameter a standard key from PSG, that is a rectangular sunk key we have selected with the width W is equal to 16 mm and thickness of the key is equal to 10 mm. So let's see whether it is sustained or not. This key will get fail or it can be sustain the torque. Okay, so the key will be considered by considering the failure of key using in a shearing. So for shearing, we need a maximum torque of the shaft, that is 663 into 10 raised to 3 Newton per mm is equal to LW pi tau into D1 by 2. So putting all the values, what we get, L is equal to 38 mm. Length is equal to 38 mm. Because we know that the width and the thickness of the key, only we need to calculate the length. Now, let us now check for the total stress in the rim, which should not be greater than the 4 megapascal. So we know that the velocity of the rim V is equal to pi dn by 60, that is 13.2 meter per second. And the total stresses in the rim is sigma is equal to sigma V plus sigma T, which is we have already minimized the equation. Okay, simplify the equation, that is tau is equal to rho v square into 0.75 plus 4.935 r divided by n square into t, where n is the number of arms. So putting all the values, what we get, the total stress developed induced is 2.4 megapascal, which is lesser than the given or design. So hence our design is safe. Okay, so in that manner we have calculated the all the dimensions based on the simple empirical relation. I hope you have understood, because it's very simple process. Equations are given appropriately, so you can just note it down the equations, fill the proper assumptions and put the values, you can get the other things. Now we will discuss one more example with respect to the four-stroke engine. Design and draw a cast iron flywheel used for four-stroke IC engine developing 180 kilowatt at 240 rpm. The hoop or centrifugal stresses developed in the flywheel is 5.2 megapascal. The total fluctuation of the speed is to be limited to 3% of the mean speed. The work done during the power stroke is 1/3 more than the average work done during the whole cycle. The maximum torque on the shaft is the twice of mean torque, and the density of the cast iron is 7,220 kg per meter square. So here the lot of empirical data is given. So each data you have to return carefully. Initially you can draw the fluctuation diagram as they have shared. In figure number 14, I have drawn the fluctuation diagram. Okay, turning moment diagram. Also, we have written the given data. Power is given is 180 kilowatt. Speed is 240 rpm. Sigma t, that is stress 5.2 megapascal. And then N1 minus N2 is given as a 3% of N, and rho is equal to 7,220 kg per meter cube. Now, first of all, let us find the maximum fluctuation of energy based on the turning moment diagram. We know that the torque transmitted by the flywheel, that is Tm, is equal to pi into 60 by 2 pi n. So P, we know that is 180 into 10 raised to 3. So the torque is obtained, calculated is 7,161 Newton meter. And the work done per cycle is nothing but the T minimum into the radian, that is theta. And here to complete the one cycle, we have to travel or rotate 4 times. So that is a 4 pi. Theta is equal to 4 pi. If we are considering two-stroke engine, then the value of theta is 2 pi. Okay, so putting all the equation, what we get, the work done per cycle is equal to 19 to 10 raised to 3 Newton per Newton meter. So since the work done during the stroke is the 1/3 more than the average work done during the whole cycle, therefore the work done during the power stroke is equal to work done per cycle plus the average work done during whole cycle, that is 9 into 10 raised to 3 plus 1/3 of 900 into 10 raised to 3. The work done during the power stroke is 120 into 10 raised to 3 Newton per Newton meter. Okay. So now during work done during the power stroke is shown in the figure by triangle ABCD, which is base AC is equal to pi radian and height is equal to T max. The work done per cycle, which we have already calculated, that is the work done per cycle we need to calculate because the number of strokes are 4, that is, but the working strokes are 2. Okay, so 4-stroke engine total rotation is to be done are 2, that is total crankshaft flywheel has been rotated, that is 720 degree. Okay, so the work done per cycle, that is P into 60 divided by N, that is number of strokes per minute, that is capital N divided by 2, that is 240 divided by 2 is a 120. So work done per cycle is 90 into 10 raised to 3 Newton meter. So work done per during power stroke 1/2 pi into T max. Now compare the equation 1 and 2. Compare the equation 1 and 2. Based on that two equations, we can calculate the maximum torque. That is 120 into 10 raised to 3 multiplied by 2 divided by pi. So maximum torque is 76.384 into 10 raised to 3 Newton meter. Now the height above the mean torque, that is GF, is equal to BF minus FG, that is a T max minus T minimum, that is T max minus T minimum mean. So the difference between that we need to calculate because that much power is excessive power. Okay, so the difference is 69.223 into 10 raised to 3 Newton meter. So now we need to calculate the maximum fluctuation of energy. Okay, so how we can calculate? By using geometrical relation, arc area of delta BDE divided by area of triangle BDE divided by area of triangle ABC, that is BG square divided by BF square. Okay, so putting the values, the area of triangle ABC is nothing but 120 into 10 raised to 3. BG is equal to 69.223 into 10 raised to 3. BF is equal to 76.384 into 10 raised to 3. So putting all the values, what we get? The maximum fluctuation of energy is 98 0.555 into 10 raised to 3 Newton meter. Okay, now the diameter of flywheel. The diameter of flywheel based on the peripheral velocity. Now we are considering the hoof stresses developed in the flywheel arm. Sorry, flywheel rim. So equation is maximum hoof stresses, that is 2.5 5.2 megapascal, that is 5.2 into 10 raised to 6 is equal to rho into velocity square, peripheral velocity square. So putting all the values, what we get, the velocity is equal to 26.8 meter per second. Now we know the peripheral velocity now, and also we have the speed, and now we can easily calculate the diameter. V is equal to pi d n by 60. Putting all the values, we can get d is equal to 2.04 meter. Now calculating the mass of flywheel. Mass of flywheel of the rim is we can calculate by the using equation of maximum fluctuation of energy. So first of all, we need to find out the value of angular speed, then the coefficient of fluctuation, and then we can easily calculate, because we know that the maximum fluctuation is 98.555 into 10 raised to 3 Newton meter. Okay, so omega we can calculate, that is angular speed of the flywheel rim is equal to 2 pi n by 60, that is 25.14 radian per second. Now the coefficient of fluctuation, n1 minus n2 divided by n, which is equal to 0.03. Okay, now putting all the values, that is delta is equal to m r square omega square cs. Now here rather expecting value the value of mass, other values are known, so putting all the values in the equation, what we get, m is equal to 4995 kg. Okay, so that much is the weight. Now next one, cross section dimensions of the rim. So as we know that t is equal to 2 times of b is equal to 2 times of t, where t is the depth, thickness of the rim, and b is the width of the rim. Now cross section area, this process is completely similar to the numerical number 1. Okay, so a is equal to b into t, b is equal to 2t, so a is equal to 2t square. Now the mass of the flywheel m is equal to area into pi d into rho. So putting all the values of known thing, what we get, thickness is equal to 235 mm and b is equal to 470 mm. Now next one, to calculate the diameter of hub and shaft. So diameter of the shaft we can calculate based on the maximum torque. So maximum torque is the 2 times of the mean torque. So mean torque is equal to 7,161 Newton meter multiplied by 2, that is making the twice of that. So 14.322 into 10 raised to 3 Newton meter, that much is the torque. So the maximum torque acting on the shaft, that is a T max is equal to pi by 16 into rho tau into d1 cube. So putting all the values, and we get the calculating the diameter, d is equal to 122. But standard nearest diameter of the shaft is 125. So we are considering the d1 is equal to 125. Now the diameter of the hub, that is a twice of d1, that is 250, and length is equal to b, that is 470 mm. Now the cross section area, cross section dimensions for arms, that cross section is elliptical one. So the major axis and minor axis relations we have already known. The number of arms which is we consider are 6. Then the bending stress of the material is 15 megapascal, which is given. Now we know that the maximum bending moment in the arm at the hub end, which is assumed as a cantilever beam, which is assumed as a cantilever beam. So capital M is equal to tau divided by Rn into bracket R capital the diameter radius of the flywheel minus radius of the shaft. So putting all the equations, what we get, the maximum bending moment M is equal to 2094.5 Newton meter. Now section modulus, how we can calculate, Z is equal to pi by 32 into B1 into A1 square. That is the equation for elliptical cross section. So putting all the values, what we get, that is the empirical relation between B and A. So section modulus will be, the equation will be resolved as 0.05 A1 cube. Now we know that the maximum bending stress allowable is 15. So sigma B is equal to M by Z. M is equal to 2094.5 into 10 raised to 3 divided by Newton meter divided by Z is equal to 0.05 A1 cube. Okay, so based on this relation, we can find out the value of A1, that is 140 mm, and B1 is equal to 70 mm. Okay, so the last point, that is a calculation of the dimension of the keys. Okay, so based on the shaft diameter, that is 125 mm, from PHG we have selected the rectangular sunk key with the width diameter W is equal to 36 mm and the thickness is equal to 20 mm. Now we need to calculate the length by considering the failure of key in shearing. So the maximum torque is equal to T max is equal to LW tau into D1 divided by 2. So putting all the equation values in equation and calculating the length, L is equal to 159. So just round up the value up to the 160. So the length of the key is 160 mm. Okay, now let's check whether the key can sustain the total stresses. So the total stresses induced in the rim which should not be greater than the 15 megapascal. Okay, so total stresses in the rim is equal to rho v square into bracket 0.75 plus 4.935 r into n square into t. So putting all the values of what we get, the total stress induced in the rim is 6.97 megapascal, so which is lesser than the 15 megapascal. Hence our design is safe. Okay, so thank you. In this the calculating the dimensions of the flywheel or a design of flywheel is very easy. Okay, you just need to understand the given data. You should use appropriate formulas for that. The procedure for, you can, if you properly observe the numerical 1 and numerical 2, the most of the process is quite similar. So I hope you have understood the design. In description box I have mentioned the theory notes of the designs, so you can refer that. If you have any doubt, you can personally call me. Okay, thank you.